In our first example, we're going to apply these 4 steps that was in our first example, we're going to apply the 4 steps that were described in the previous video by calculating the total resistance, determining the total current, applying that current to all resistors in this series circuit, and then calculating the remaining factors, the voltage drops, the power for each resistor. So one of the things you'll see me use quite frequently is what I call a Verb table. It's a table that keeps us organized when we're trying to determine the voltage, current, resistance, and power across each resistor, hence the VIRP acronym. So you'll fill out the table, you'll set the table up as such, and we will fill in the resistor values. So we have R1 and R2, so we'll simply call them R1 and R2. We know that they are 8 ohms and 2 ohms respectively, and we know that the voltage for the whole circuit is 40 volts, so I'll plug in my known values, the voltage and the individual resistances of those resistors. Now we identify that this is a series circuit, so we know that the total resistance in a series circuit is simply the sum of all the resistances. So we realize here that 8 plus 2 gives us 10, so I can put that down for the total resistance of the entire circuit. Now, anytime you have any 2 values in any one row, you can always apply one of the equations we've discussed previously. In this case, we can actually realize that by knowing the voltage is 40 and the resistance is 10, we can utilize Ohm's law. Okay, so the voltage of 40 and the resistance of 10 produces a total current of 4. So utilizing Ohm's law, we recognize that the total current coming out of the battery is 4 amps. Well, this is a series circuit, so I know that the current is the same everywhere because if 4 amps leaves the battery, there's only one pathway. 4 amps must go through the 8 ohm resistor, 4 amps must go through the 2 ohm resistor, 4 amps must arrive at the positive terminal of the battery on the other side. So I can actually just fill out the entire current column because I know that in a series circuit, the current is always the same. Now all that's left is to basically calculate my remaining voltages and my remaining powers. So the voltages can be calculated using Ohm's law for the individual resistors. I have the current and the resistance of each, so I can multiply I times R. And in the first case, I get 32, and in the second case, I get 8. Much like I applied Ohm's law to the total circuit on the bottom, I can apply it individually to the 8 and the 2 ohm resistor. And now that I have voltage, current, and resistance, I can apply any of our power equations. P equals IV, P equals I squared R, P equals V squared over R, whichever ones you would prefer. I typically do IV because it's a little bit more straightforward. And when I do so, running down the list, I get powers of 128 watts, 32 watts, and 160 watts respectively. So this table allows me to calculate a bunch of information for every individual resistor as well as the total circuit. And now I'll be able to kind of pick and choose what values I need based on the questions being asked of me. One really quick way to look at this is the self-check. You can pretty much tell if you've done this correctly because the voltage drop must be the entirety of the voltage you have by the time you get to the other terminal of the battery, no matter which pathway you take. So if we realize that in order to go through this circuit, I must pass through the 8 ohm resistor, which as you can see in the voltage column, quote unquote, costs me 32 volts. I then must pass through the 2 ohm resistor, which costs me 8. You'll see that the amount of voltage that I drop or that I quote unquote spend in total between those two is 40. Well, if I started with 40 and I spent 40, I will get back to the positive terminal on the other side with 0. And if I've spent all my voltage, or better to say, all my voltage has dropped, by the time I get to the other terminal, I know the odds of me doing this problem correctly are somewhere in the ballpark 99%.